Welcome, folks. A video on inverse functions. In this video, we'll be discussing the following questions. Given a function f, does it have an inverse function? And if it does have an inverse function, is that inverse function differentiable? And if so, how can we find the derivative? So we'll start off with some background, talk a little bit about inverses and how to find them. We'll find a couple inverses and then we'll talk about doing calculus on inverses. So start off with the definition of one-to-one. We say that a function is one-to-one if it never takes the same value twice. So if x1 and x2 are different, then the function values at x1 and x2 are also different. So here's an example of a function that is not one-to-one. We can quickly show that this function is not one-to-one, f of x equals x squared plus 1, by choosing two values that are different and plugging them into the function and showing that we get the same value. So here we see with x1 equal to 1 and x2 equal to minus 1, the function values at x1 and x2 are the same, right? When you plug those in, you get 2. So x1 and x2 are different, but f of x1 is equal to f of x2. A graphical interpretation of one-to-one is that when a function is one-to-one, no horizontal line intersects the graph more than once. This is the so-called horizontal line test, and if you can find any horizontal line that intersects the graph of a function more than once, we say the graph or the function is not one-to-one. So we can use this test on our previous function, so verify that the graph of this function x squared plus 1 fails a horizontal line test. So we'll start off with a graph of this. Everyone knows that the graph of a quadratic is just a parabola, and in this particular case, the plus 1 shifts that parabola up 1 unit on the y-axis. So here's that parabola shifted up by 1 unit on the y-axis, and we can see that choosing a horizontal line strategically, like this one, that horizontal line intersects the graph more than once. So the graph of this function fails the horizontal line test. We can see that the function is not one-to-one. In general, when functions are one-to-one, then they have an inverse. So if a function is one-to-one, it has an inverse. Then the notation that we use is the following. We say that the function f has inverse f to the minus 1. The relationship between the function is that whenever y equals f of x, x is equal to f inverse of y. And the domain of the inverse is the range of the original function. The range of the inverse is the domain of the original function. A real quick observation about a notation alert. This minus 1 power is used to denote the inverse. However, it does not mean a reciprocal. So if you do want to denote the reciprocal of a function, we're going to express it as f of x all to the minus 1 power. Okay, so again, here the notation denotes inverse function. So let's go ahead and talk about finding inverses and finding a couple. Here's a general strategy to find an inverse function given a one-to-one function x. So we'll start off by writing y equals f of x. If possible, solve for x, and then exchange x and y, and the thing sitting in front of you should be the inverse function. So here's an example. Let's go ahead and have a look at the function f of x equals x times 4 minus x on the interval x less than or equal to 2. So the first thing we'll do is verify that this function is invertible by showing that the graph of the function is one-to-one. Now this function has sort of an unusual domain. It has a domain x less than or equal to 2. So we'll start off by graphing the function on its natural domain and then restrict the domain to x less than or equal to 2. So on the left, we see the graph of the function x times 4 minus x. It's a parabola that opens down with intersections at 4 and 0. And of course, if we are to restrict that function to the domain x less than or equal to 2, you can see that we just get half of the parabola. And this definitely passes the horizontal line test. So the function x times 4 minus x on the domain x less than or equal to 2 is invertible. And here we see just a little bit better graph of that function. Okay, let's go ahead and find an expression for the inverse, and we'll identify the domain and range of that inverse. We can see here that the domain of the function, of course, is x less than or equal to 2, and it looks like the range of the function is y less than or equal to 4. We'll see in a minute how the domain and range of the function f come into play in finding the domain and range of the inverse. Okay, so like we mentioned, we'll go ahead and write y equals f of x, try to solve for x, and then interchange x and y, and that inverse should be sitting right in front of us. So again, we'll start by writing y equals f of x, solve for x. In this example, I've completed the square to do that. We end up with an expression here that's of the form x minus 2 quantity squared equals something. In undoing that square, we'll go ahead and choose the negative branch of the square root because we expect the domain of f to have x less than or equal to 2. So choosing the negative branch, we can solve for x as 2 minus the square root of 4 minus y. Switch y equals y and x, and we see the inverse function right there sitting in front of us. So there's the inverse function. F inverse of x is 2 minus the quantity square root 4 minus x. Now the graph of that function isn't so bad. It's just a square root function that's shifted and translated around a little bit. So we can see that here in blue, and we can see that the domain of the inverse function is x less than or equal to 4, and the range of the inverse function is y less or equal to 2. So this domain and range is exactly what we expect from our definition. And we can see sort of that in order to graph the inverse, the x values and the y values switch. So any value that's on the graph of the function, if that value is a, b, like this one, as an illustrating example, I'll go ahead and take the value to be 1, 3. Then the value ba, or in this case 3, 1, is on the graph of the inverse. Okay, that's no coincidence, and it happens exactly because the inverse sort of switches the value. So that's the inverse relationship that we expect to have. And this is true in general, that in general, the graph of the inverse function is the graph of the function reflected about the line y equals x. So you can always use that graphical understanding to find the graph of an inverse given the graph of a function. Okay, let's go ahead and talk about doing some calculus on inverses. So it turns out that when a function is one-to-one and continuous on some interval, then the inverse function is one-to-one and continuous on the corresponding interval. And when f is one-to-one and differentiable on an interval, and that derivative is not 0, then f inverse is also differentiable at a. I should say a here, not on an interval. So let me fix that. So the intuition here is that due to the fact that inverses have graphs that are reflected about the line y equals x, any horizontal tangent in the graph of f, right, when the derivative is 0, becomes a vertical tangent in the graph of f inverse. So we just want to avoid those points to ensure that our inverse function is differentiable. Okay, in that case, it turns out that the derivative of the inverse evaluated at a is 1 over the derivative of the function evaluated at f inverse of a. And this is fairly quick to see if you think about the relationship y equals f inverse of x, and then try to find the derivative dy dx. So the first step in doing this is to write down the relationship between the function as inverse y equals f of x, f inverse of x, and then to write down the corresponding inverse relationship. So I'm going to refer to this as the inverse relationship, x equals f of y. Now that, of course, we can differentiate using implicit differentiation. So differentiating implicitly, we can see that the relationship x equals f of y gives us 1 equals f prime of y times dy dx, or solving for dy dx, we see that dy dx is 1 over f prime of y. And now, as long as we can remember what y was originally, y is f inverse of x, we can go ahead and solve for dy dx. So again, here's that expression for the derivative. The derivative of the inverse f inverse prime is 1 over f prime of f inverse of x. And again, this is true whenever the derivative is not 0, right? So we have to have a non-zero derivative for this to be true. And this is a strategy we're going to use pretty frequently. Okay, let's go ahead and have a look at an example. So here is the inverse function we looked at previously, and we'll find the derivative of this inverse function two ways. First, directly, and then second, using the theorem we had before. So directly, we can find the derivative f inverse prime just by using our rules from Calculus 1. So just by using the power and chain rule, we can see that the derivative of the inverse is negative 1/2 times 4 minus x to the minus 1/2 all times minus 1, or if you simplify the minus signs, we end up with 1/2 times the quantity 4 minus x to the minus 1/2. Now here we're interested in f inverse of 2, so just plug in 2. So plugging in 2 to the derivative of the inverse, we can see that the derivative of the inverse at 2 is 1 over the quantity 2 square root of 2. Now we can also use our relationship between the inverse of the derivative and the derivative of the inverse to find this value. So we can find this indirectly using the composition f prime of f inverse. So to start off, I'll remind you that we're trying to use this formula. F inverse prime at A is 1 over f prime of f inverse of A. And the first thing we need here is the value of the function at f inverse at A. So we're trying to solve for this function B. And we can see that if we plug in f of b equals 2, then we can solve for the b as 2 minus the square root of 2. So here we can see that f prime can be computed quickly. And once we compute that derivative, we can quickly plug in the value of b at 2 minus root 2, take 1 over f prime of f inverse of A, so 1 over 2 root 2, and we get the same thing. So the point of this example, and this is pretty cool, is that we actually didn't ever need an expression for f inverse in order to find its derivative at a value. Okay, that's it for this section on inverse functions, folks. Have a great day, and we'll see you next time. Bye-bye.